Come light it up, I'm ready to go. Come light it up, come light it up, I'm ready to go. Come light it up,
Thanks everyone for joining this session. We're going to talk about one of the most transformative features that we worked on for Trino in the past couple of years. I'm here with Dane and Dave. Well, Dane and Dave are here joining me in virtually in the chat. They will be answering questions in the chat, and then later, when we finish, they'll be joining live on the Zoom stream. Oh, there they are. Say hi, Dane, David. All right, so we're going to talk a bit about how we got here, the history of Trino, how we created it, how we got to the point of being able to use it for big batch and ETL workloads. We'll talk a bit about some of the challenges of the previous architecture, what we tried to do with after we implemented all the new capabilities, what were the goals, and the architecture that helped us solve those challenges. And then we're going to conclude with talking about some of the future opportunities and possibilities of what will come after after we keep going with development of this feature. And then at the end, of course, Dane and David will be live answering questions with me. Back in 2012, when we created Trino at Facebook, the initial goal was to replace Hive as an interactive query engine. People were using it were using Hive for interactive queries, but those were pretty slow. So we were trying to tackle that use case. How do we get people to be able to query quickly, iterate over the results, and keep going? And then that was pretty transformative at Facebook. We basically enable data engineers to run analysis much more quickly. And some of them said, OK, well, if I can do this with interactive queries, why can't I do this with my batch ETL workloads? So we saw some people, kind of grassroots efforts, where they started using Trino itself for batch workloads in the kind of developing pipelines, data transformation pipelines, using Trino directly. And this was not something we meant to tackle in the beginning, but it just happened organically. And then by the end of around 2018, around 2017, we said, OK, we're seeing a lot of people interested in being able to do their work in Trino. And we set up a project, an effort to actively start replacing Hive with Trino as a way to implement data transformation pipelines and ETL workloads. And by the end of 2018, we had about 50% of all the ETL workloads at Facebook and 85% of all the new workloads running on Trino. So it was very, very popular, very transformative for the organization at that point. I mean, it worked really well, like for those existing workloads. And of course, some of the reasons people decided to adopt that Trino for that type of workload is Trino was faster, much faster than Hive. And then they also got to use the same language for their ETL pipelines and their interactive workloads. They could develop their pipelines interactively, try them, test them, and then once they were comfortable, confident with the results, they could just create a corresponding pipeline with them. So that ease of use, ease of switching between the two environments was one of the biggest drivers. But there were a number of challenges. Trino was originally designed for very fast interactive queries, and it did great at those ETL workloads, but there were some limits that it occasionally hit. And one of those limits is what we call the memory wall. That means that you run a query, as long as the working set required by the query fits in memory, everything is great. The query runs fast, runs to completion, you see your results. But if your data set grows, or if there are capacity constraints in your cluster, then the query might just fail. So it's either it works or it fails. And the only way to deal with that is either you optimize your query, rewrite your query, break it up into pieces, or you have to scale your cluster accordingly. And sometimes that's too cost prohibitive. One of the things you occasionally, companies, organizations don't want to do is to have big clusters just to satisfy a few queries, and then those clusters sit idle the rest of the time. So having a more flexible strategy there is important. And that was one of the challenges of the previous architecture. The second one is that queries in Trino had to run to completion. They had to start running and complete, or if there was a failure in the middle, the whole query would fail. There was no way to restart from where the query left. There's no way to reuse the computation that had been previously performed in the case of a failure. So, which is fine for short queries. You can retry many times and still be below the time it would take to run an equivalent height query, for instance. But it's wasteful. Like the longer the query runs, the bigger the query is. When there's a failure, the higher the chance of losing a bunch of work that you had to redo. So it's a waste of resources and time. And then, of course, there are issues with resource management. When the clusters are resource constrained, you have to tune them very, very carefully, make sure that the working set for all the queries that are going to be running concurrently fits in memory. And that requires skilled engineers managing those clusters and tuning for the workloads that are running on them. And you have to monitor them. You have to be aware of how to operate those clusters. So those are challenges that make it harder for the previous architecture of Trino to support these bigger ETL workloads. So, and kind of to illustrate why that happens, like this is a depiction of the previous architecture. So queries are planned as effectively a network of tasks where data from upstream task flows as it gets processed to downstream tasks, and it gets consumed and forwarded on to the next task. And all the tasks need to be running at all times while the query is running, which means that if all the data needs to be held in memory, all the working set needs to be held in memory, and if anything fails in the middle, you have to restart the whole pipeline because some data may have already been consumed by downstream tasks. So you cannot, there's no mechanism to tell downstream tasks, hey, you already seen this, I'm gonna recompute it, so this is the same result computed again. So, this is kind of the key or the core of why this is Trino had those limitations. Of course, advantages are that the query runs as a full pipeline. Data goes from source stages all the way to the end very quickly, depending on the shape of the query, and queries can finish very quickly. So low latency is very fast. There's no I/O in the middle, so that's what gives Trino its speed and power. So about a year and a half ago, we started looking at this problem of how do we get Trino to the next level? How do we make it work better in the face of failures? And we started this project. We rolled it out about sometime last year, and we've been making improvements since. So some of the goals of this project, as you can imagine, well, the first one, the most immediate, obvious one is we want Trino to be able to tolerate individual task failures. So if a node fails, we need to be able to continue processing, recover, reuse the computation that has already been performed to be able to complete the query faster and be able to waste fewer resources. So that's what everyone that thinks about fault-tolerant execution thinks about. But there are other goals. One of the goals is being able to run queries of any size. As I mentioned before, the working set of the query need to fit in memory in the previous architecture. With the new architecture, we can run queries without having the whole working set in memory. We can stage it. We can run pieces of the query in chunks in a way that allows Trino to be scaled. It can be scaled as small or as large as a user wants, based on how much they're willing to spend on hardware, resources, and so on. And then because queries get split into smaller tasks, one of the goals was to be able to have the ability to have more flexible strategies for managing resources. Like, how do we take advantage of being able to prioritize pieces of queries depending on how important the queries are, be able to run one query faster. Say a higher priority query shows up, what do you do? Do you pause the existing query? Do you keep going? Do you let the new query, do you cancel the first query and let the second query go? So having more control over that is important, especially for clusters where you have a lot of users with different priority workloads and so on. And then finally, like one big goal is, like, we started thinking about, okay, how can we take advantage of what goes on during the query execution to adapt the execution dynamically? Like, there's lots of things that Trino can do to adapt to different running conditions. Like, if you add more nodes, some parts of the query can scale up. But there are some things that it cannot do. For example, it has to plan the query up front, and it can use statistics and cost estimations to figure out what is the best strategy. But that strategy may not be the right one, depending on the actual shape of the data. That it's hard to know in advance. So being able to dynamically adapt as the query goes, being able to start a query, then observe what's going on, and then readjust the plan, readjust the execution strategy, is a very powerful concept. And one of the goals is that we said when we started the project is to see how can we take advantage of a new architecture to enable this capability. So as you can see, this is the architecture of what we call the fault-tolerant execution architecture. The difference between the previous architecture is that between stages of the query, there are persistent buffers where intermediate data is stored. And that's implemented in a way that, so the idea is, a stage runs, the intermediates get persisted, then the second stage can read that data, process, and so on. If something fails in the middle, you can recover by reading those intermediate results that were computed. Those buffers are created, they are abstracted in the engine. So there's an interface that plugins can then implement to have different flavors of how those buffers work. Right now, we have buffers that work on object storage, on Google Cloud Storage, Azure, AWS, and S3. But the strategy is pluggable. Anyone can go implement their own variant. You can implement a buffer that's based on local disk, SSD, hierarchical storage. The possibilities are endless. And of course, the key here is that any task can stop and start again, and you don't need to recompute all the results that the previous stages already produced. So, of course, we can talk about some of the benefits. If you think about task being, the engine being able to stop and start, or being able to recover from the failure of a single task, you can see how, let's say, if you look at this chart, let's say you run stage one, that completed, all the intermediates got stored in that exchange buffer at the bottom. Then you start running stage two, and one of the tasks fails. You don't need to go and recompute stage one, as in the previous architecture. You can restart that task and read from the intermediates. So that means that all the computation that was performed in stage one is still valid, it's still reusable, and the engine keeps going from where it left. So there's reduced computation. Of course, because you don't have to recompute stage one, the query takes less time to complete. If you consider the end-to-end of you submit your query, you wait for it to complete, and then you see a failure and you have to restart your query. If you have to keep doing that, then the end-to-end time is going to be reduced because the query, first of all, it retries automatically, and second, it continues where it left off. So there's the end-to-end latency of the job is lower. And the other thing that I mentioned before, because the working set doesn't need to fit in memory, because you don't need to schedule, for example, if you look at stage 2, you don't need to schedule task 1, 2, and 3 at the same time. You can start with task 1 if you are memory constrained. Then when task 1 completes, then you can start task 2. And then when it completes, you can start task 3. So the amount of memory you need is the memory that a single task needs. Or if you have memory available, you can run multiple tasks at the same time to fit that memory profile. So that's what gives now Trino the ability to accommodate the queries based on the amount of memory it has. And of course, there will be, if you have less memory available, the queries will take longer because you have to sequence the execution of the tasks as opposed to run them in parallel. But you have that trade-off. You can trade off the amount of memory you have with the execution. And so looking forward, there are a number of, so everything I talked about is already in the code base. It's available, people can use. We're now starting to look at kind of the future of what are the things that we can do going forward. And of course, now we have the two architectures. The two architectures or modes of execution coexist. You can turn one or the other with configuration options. One of the things we're looking towards is unifying those two models. And one of the key elements is being able to do speculative execution, where instead of doing one stage at a time, we can schedule parts of downstream stages with the hopes that, in general, queries are not going to fail, tasks are not going to fail. So if everything goes well, then the query will complete fast, and as fast as it completes in the previous architecture. And if there's a failure, of course, you're going to have to recover. But that ability to speculate and run downstream tasks and stages early on is what kind of bridges the gap between the old architecture and the new architecture. And then once we have a unified architecture, you can start applying all the techniques, like, for example, being able to tolerate failures allows you to run on spot instances without, spot instances are cheaper instances in AWS, or there's the equivalent concept in Google Cloud Storage. So you can run those instances to get a lower cost and not be affected by failures in the ways that the previous architecture was affected. So you can take advantage of those same techniques for interactive workloads, and that's super powerful. It's like if every installation of Trino can run in that mode, then you have more flexibility in terms of managing costs for ETL and for interactive workloads. You can scale your computation or your clusters up and down depending on how much you're willing to pay in terms of infrastructure at a given point in time, or in response to the workloads. You can have a small cluster, and as new queries show up and as tasks start getting queued up, you have the Trino has more visibility into what's going on, and you can build infrastructure to scale up your cluster to deal with that demand. And then I mentioned before, like the ability to replan and adapt your query execution based on what's going on in the initial stages of a query, or as a query executes, being able to observe the shape of the data, the statistics at runtime, and so on, and be able to replan and re-optimize the query is one of the things we're going to start looking at, and it will open up the doors for more powerful techniques. And schedule and resource scheduling is the obvious one. Being able to choose which parts of the queries get executed at a given point in time, which ones get prioritized, It gives it's like another superpower that we can give to Trino. That right now, because queries need to consume resources, memory resources in the cluster, there's an incentive for queries to complete as quickly as possible. With this architecture, we can now have more flexible options here. We can park queries, we can prioritize certain tasks, and we can apply different policies depending on what the user is trying to achieve and what the administrators are trying to achieve in terms of their installation. So what we built, I think is a fantastic capability, fantastic feature. It's not something I had imagined, or I'm pretty sure Dean or David hadn't imagined that we would ever get, or for a long time we're getting Trino. And I'm actually super excited that we finally got that implemented. And I think it's going to be the next step. It's one of those things that transform Trino into a completely different thing, and it's going to be the next step in the capabilities and evolution of Trino. So if you want to try it out, you can. There's if you scan those QR codes, there's a repo with a tutorial for how to set it up on your own, how to set up fault-tolerant execution in using cloud storage in your own cluster. Or alternatively, you can sign up for Galaxy. That's the second QR code there. And you can try this feature today in Galaxy, Starburst Galaxy. So with that, if you want to get involved in the project, of course, we can join us on Slack. You can contribute to pull requests or code issues. If you want to try this feature and you find issues, please let us know, file an issue, and we have a bunch of people actively working on it. They will respond and help you and fix those issues. So you can find us on Slack if you have questions. And I think with that, we're done. So now we have Dana and David here. If we have any questions, we're going to answer them now. All right, so let's look at the question. So first question is, how is Trino comparable with Presto for parallel querying of long-running queries? What could be done to improve the performance of a dashboard with multiple queries sent to Trino cluster? So I will say this feature, the fault-tolerant execution, is exclusive in Trino. So if you're running Presto, you won't have that. Presto has an alternative implementation where it can use Spark as a backend, but with Trino you don't need to run a separate compute engine for that. It's all built into Trino itself. So you can just run one installation, and you get the best of both worlds. You get the SQL language from Trino, you get the ability to run interactive queries, and the ability to run batch ETL workloads in a single installation.
Yeah, I'm also not sure that. So this question really gets at dashboards, which are typically about having extremely low latency, typically low compute queries, and that's kind of a different use case from large ETLs that you expect to run for a long time. Typically, parallel dashboard queries are better served by the sort of existing model we have. So as part of Martin mentioned, the long-term goals of this is to actually figure out how to combine the two models and have the system be able to smartly adapt between the two as the systems are running. So you don't have to pick ahead of time which model you're running in.
Yeah, and that ties into the next question, which says, can't fault-tolerant execution be enabled for specific resource groups? For example, users that have long-running queries, or is it a cluster-wide setting? Right now, it is a cluster-wide setting. You have to enable it for the whole cluster. So one of the things we recommend for the time being is if you're going to run batch ETL workloads, set up a cluster dedicated to that. If you want to run interactive workloads, set up a different cluster. The trade-offs that you make in each of those are generally different. In one, you're going to be optimizing for low latency. For interactive queries, you're optimizing for low latency. You might be over provisioning so that people have a good experience. If they submit a query, they get a response, or the query starts running as soon as possible. For fault tolerant or batch workloads, you may be more resource constrained, or your workloads may show up all at the same time. So you have a different set of constraints. You might be willing to wait longer for some of them, and so on. This is actually how we used to run it when we're at Facebook. So it's still a good strategy until we end up unifying both models and make the system more flexible. Right, third one. Is there a way Trino can leverage the auto-scaling feature of Kubernetes to add more spot nodes in case the query needs more memory or compute? Dane or David, do you want to take that one?
So today, we're sort of in the early days of this feature. So absolutely, this is something we want to be able to do. When you're using fault-tolerant execution, you can, the important number is how many queued tasks you have, basically tasks that could run if you had more resources. And based on monitoring that, you can absolutely scale up and down the system.
All right. So the next one is, are task outputs and buffers serialized in a comprehensible format like ORC, Parquet, or JSON, or is it some binary format intended just for this use case? Well, Dane or David, you want to take that, or?
I believe the answer to this is, from the engine's perspective, there's an API. And the API is, I give you data, and later I'm going to ask for it back out. I'm actually not sure what the existing implementation does. And it doesn't really matter because these are short-lived in the grand scheme of things. They're designed to just be held for that specific query.
I would assume it's serialized pages similar to how Trino transports data between workers already.
Yeah, so Trino has an in-memory format for data pages, and it has a format for exchanging pages across workers, is what the existing or the previous architecture used. So in this new mode, it's just a serialized form. It is a persistent form of those same serialization formats.
Oh yeah. Additionally, they are compressed and encrypted on a per query basis. So you couldn't share them across queries even if you wanted to, in the current implementation that exists underneath the abstract APIs.
Right, next one. With fault-tolerant execution, do intermediate results between stages need to fit entirely in memory, or is it the case that intermediate results are persisted as they are generated to reduce memory pressure? So the intermediate results don't need to fit in memory. I mean, as they get produced by tasks, they are persisted in the intermediate storage, and that storage can be, like as I mentioned the talk and then just say it again, it's an interface. So it's an interface that the engine talks to, and the implementation can do anything it wants. It could be object storage, it could be local disks, it could be memory. Like if you want intermediate buffer that is in memory with offloading to object storage for performance, you could implement that too. But it doesn't need to fit in memory. So that's kind of the whole point of this, is that, or part of the point is that we can execute queries in memory constrained environments, and you can trade off the performance based on how much memory you have versus how much you're willing to offload to storage. Right. I think, okay, one more, and then I think we're out of time here. So what is the performance trade-offs when using exchange pooling that is backed by NVMs or SSDs and traditional storage? Dane or David, you want to take that one?
It's going to come down to I/O. So NVM, you can compared to a traditional disk, has effectively infinite I/O operations. Traditional disk has like 1 T per second. So if you're going to have reasonably high concurrency, you run out of I/O operations pretty quickly with traditional disks, unless you happen to have lots of spindles. So it is possible that in your larger disk installation environment, you have so many spindles that you have enough I/O to be able to handle the intermediate workloads. It's possible you don't. Obviously, NVMe is typically a lot smaller than traditional disks, so it becomes complicated.
All right, I think we're out of time here. So thanks everyone for joining. And again, if you want to try this feature, give it a go and ping us on Slack or on GitHub if you have problems or questions. Thank you.